All right, so we've talked about the outer ear or external ear and the middle ear, and now we're going to spend a fair bit of time on the inner ear or internal ear. And we're not looking at the entire inner ear. Physiologically speaking, that also includes some structures to do with balance. We're just looking at the cochlea here, essentially. And so here is a new image, and this is we can see in this image the outer ear through to the middle ear with the tympanic membrane, the eardrum, the ossicles through to the oval window. And then on the other side of the oval window, we have, here it's depicted straight. The cochlea is actually curled up, but it's convenient to straighten it out to illustrate some of the structures. The sound, having been transmitted through air and then through the ossicles, now comes into this liquid, and it gets transmitted down the cochlea on one side of our basilar membrane, which sort of goes down the middle of the cochlea, along one side, and then around the end, the helicotrema, just the apex of the cochlea, and then back up the other side to the round window. It can also be transmitted along the way. Some of the sound gets transmitted across the basilar membrane. So just a little bit more structures here. This first passage is called the scala vestibuli, or the vestibular duct, vestibular canal. And then on the bottom, we have the tympanic canal, or the scala tympani. And in the middle, we have the basilar membrane, which also has the scala media, or the cochlear duct, as part of it. And we'll see that in the next image that we get to. And generally sound travels much faster through a liquid than through air. In air, remember, sound travels, about 345 meters per second. In the perilymph, this fluid that fills the cochlea, it travels about 1,500 meters per second. So like 4 or 5 times as fast. That's all right. And as the sound is traveling up and down the cochlea, up the scala vestibuli and down the scala tympani, it's affecting that basilar membrane in a way that gets translated into neural impulses. And the auditory nerve is connected to the basilar membrane through the cochlear duct that we're about to see. And that's what we hear. That's the neural impulses that tell our brains what we're hearing, or depending on your philosophical perspective, that the neural impulses that are us hearing. Okay, so let's get a little bit deeper into it. So here is the internal structure of that cochlear duct. So this is essentially a cross section of what we just saw from the side. So here's the scala vestibuli, the upper duct, and the lower duct, the scala tympani, and here's the cochlear duct in between, attached to the basilar membrane here. And in this we have a structure called the organ of Corti, and it has some outer hair cells, some inner hair cells, this tectorial membrane, and then it's all attached to some nerves. That's the nerves are the yellowy orange structure here. Okay, so what's going on? Well, the idea is that as sound travels into the cochlea, it encounters the basilar membrane. Now, once upon a time, at one point, there was a hypothesis, a theory, that maybe the basilar membrane is some kind of resonating structure, and different parts of it will resonate with different frequencies. So if this part resonates with a frequency, that'll be transmitted to the nerve fibers that are attached to it, and those nerve fibers will tell us, that's a middle C, or that's a 1035 hertz, or whatever it is. And then if it's somewhere else, it'll tell us it's a higher pitch or a lower pitch, that kind of thing. And that seemed plausible, but then it was realized one thing that we need to have with the basilar membrane is it needs to be highly damped. If you remember damping from a previous module of this course, damping is how quickly a sound dies away in a structure once the source of that energy is withdrawn. So something that isn't very highly damped, like a tuning fork or one of those fine goblets, it'll keep humming after you stop singing the note, or after you tap it, it'll keep going for a long time. We don't want our auditory system to do that. As soon as the sound in the world stops, we want it to tell our brain, oh, that sound stopped. We want the energy to dissipate right away so the information going to our brain is updated as quickly as possible. So it needs to be highly damped. And one of the things about a highly damped structure is that it's not as focused in its frequency response. Right? So the tuning fork, very little damping, very high focus frequency response. It vibrates basically just at that narrow frequency that you're after. The more damped something is, the more its vibrations spread across multiple frequencies. And so the highly damped, the basilar membrane, we need it to be highly damped, so it gives us that up-to-the-date information about what's going on in our acoustic world. It means no part of it can be very finely tuned to a particular frequency. So this resonance theory of speech perception just doesn't wash. It can't give us the kind of hearing that we need. So what we have is this traveling wave theory. So let's call up an image of that. Here's a sort of a schematic depiction of that. Sound comes in through the oval window, and as it's coming along, as it's traveling along the vestibular duct there at the top, it sets up this traveling wave in the basilar membrane. The basilar membrane starts vibrating up and down, and the basilar membrane isn't uniform along its entire length, so it happens to vibrate better with high frequencies at the short near the base, and better with low frequencies near the apex, away from the oval and round windows. But really, it's vibrating along the whole length, and you see that this traveling wave, although the sound is a longitudinal wave, this traveling wave in the basilar membrane is a transverse wave. It's going up and down. And as it's going up and down, you can think, here's where the cochlear duct is, right? With the organ of Corti, the thing that's actually connected to our brain wiring, to the nerves. As the basilar membrane is doing this, it's doing some twisting relative to that structure, that cochlear duct. And that twisting means that let me get back to our image. This organ of Corti, with the tectorial membrane on the top and the outer and inner hair cells here, those are going to rub against each other because you've got this twisting. So these structures are kind of going to rub against each other. And that movement is what stimulates the hair cells, the inner hair cells. They get moved and stimulated, and that fires off those nerve impulses that tells the brain, hey, there's a sound happening here. Okay, there's a bit more happening. You can read in the textbook about what the outer hair cells do to respond to that sound, to reinforce it, or in some cases to damp it down. They actually can affect the movement of that structure. And there we have it. And so, to a certain extent, different areas of the basilar membrane do respond to different frequencies because of their different amounts of stiffness and whatnot. But also the amount of vibration, like how that vibration, that traveling wave, will be faster or slower depending on the frequency of the sound that's coming in. And those individual nerve cells will respond faster or slower depending on how quickly they're being moved back and forth. So it's a complex combination of things that affect, where is the hair cell, as well as how much is it moving back and forth with this traveling wave that generates the pattern of neural signals that tells our brain, hey, there's some high frequency stuff here and not a lot of low frequency, or vice versa, or what is the frequency composition of this sound. Okay, and I do encourage you, I'm kind of talking through in a very general sense how this works. I encourage you to look in the textbook to get some of the more nitty-gritty details. And there is other stuff happening. For example, those outer hair cells that can respond to air, the sound comes in, things get moved around, the brain can actually send signals to them to respond to the sound, to maybe damp something down or reinforce if it's an interesting sound from the perspective of our auditory system. And that actually gives rise to these what are called autoacoustic emissions, OTO, auto. Yeah, I know my variety of English doesn't have quite as many vowels in that region as other varieties. So anyway, autoacoustic emissions that in particular circumstances can actually be detected. If you send a sound signal into the ear and you have a sensitive enough microphone attached, then the sound, remember, it's going to whip around really fast, right? The auditory canal is really small, the middle ear is very small, and the cochlea, which is huge, it's like 3.5 centimeters long if you unwind it or something, but sound travels along it really fast because it's this high speed liquid. The sound will actually, it kind of comes around really fast, but those extra actions that need the time for the nerves impulses from the inner hair cells to go up to the brain and then a signal to come back to stimulate those outer hair cells. So there's a delay. So after the sound has sort of bounced around a little bit, there's this other thing that happens, and so you can actually detect it. And there are hearing tests that are even applied to newborn infants that can detect, hey, is everything connected along this chain if we hear this autoacoustic emission coming back at the appropriate time? So that's kind of exciting. All right. I think that's enough. There's a lot of stuff happening in the inner ear. And like I said, do dig into the details in the textbook and other resources as you can. And in the next video, we will look at the psychophysics of it, the perceptual correlates of our physical acoustic characteristics that we were looking at a few weeks ago. All right.